cloud, blah, blah, blah. There we go. All right, so I gotta click on that. Okay, so let's all go to the end of the packet and look at the supplemental information to make sure we're utilizing our resources effectively and that we don't spend a lot of time looking for equations that we want to use or looking for equations that you aren't given. 50 minutes isn't that much time. I don't want you to spend a lot of time looking for information. We should know where that information is. So let's look at this. We give you a bunch of constants. So Avogadro's number, but I hope at this time you know what that is. We give you the two types of gas constants, though in this chapter, 16 and 17, we don't really use R, I think, at all. Kelvin conversions, Fahrenheit to Celsius, doubt that you'll use that. Here are pressure conversions. And then here's the important one. This is the ion product of water, so the kW. So 1 times 10 to the negative 14, but this is only good at 25 degrees Celsius. So if we don't give you a temperature, assume it means we're at 25 degrees Celsius. So unless we give you a different temperature, we would give you a different kW for that temperature. But for 99% of the questions that we do on this exam and the final, we will use 1 times 10 to the negative 14. So at this point, I hope that you already know what kW is and that actually giving it to you isn't going to help you that much. Some equations that we give you, the quadratic formula. Though, again, in this class, you can always make an approximation, right? Always. So using the quadratic formula will just get you a more correct answer. But if you use a valid approximation, you should get an answer that's close enough to the tolerance of your choices on the exam. So do keep that in mind. I haven't actually used the quadratic formula in a long time. Other equations are the percent ionization equation and pH for a buffer. This is the pH or the Henderson-Hasselbalch equation that is only good for buffer solutions. So this was asked of the exam last time, but I didn't go over it. Let's on the previous midterm packet, I showed what was called the magic square. The magic square is not very magic. I just want to show show how all of the equations relate to one another. So we talk about pH, we talk about H+ concentration, we talk about all these things. How would the questions use Avogadro? I don't think the exam will use the Avogadro's number. We give you everything. These fundamental constants don't change from midterm to midterm. We give it to you just in case you need to use it. Again, I was mentioning the magic square. This was from last time, but I never actually specifically described what this magic square is. I don't know why it's magic. It just is. So this square relates 4 different properties of water. The first one is H+ concentration and OH- concentration in a sample of water. It doesn't even have to be pure water. It can be any aqueous sample. Both of these values are related to each other by what constant? kW. So kW equals H+ concentration times hydroxide concentration for any sample. It could be an acidic sample. It could be a basic sample. It doesn't matter. How much H+ and how much hydroxide are present in that sample are related by kW. And we know what kW is at 25 degrees Celsius. It's 1 times 10 to the negative 14, right? So this number, let's pretend this magic square is at 25 degrees Celsius. That's how those two values are related to one another. All right, how do we go from H+ concentration to pH? What do we do? Negative log. So if we take the negative log of the H+ concentration, we can get pH. But then how do we undo a pH to get back to H+ concentration? 10 to the negative pH, perfect, right? Same thing for hydroxide. To go to POH, we take the negative log of the H+ concentration, so negative log of that. But if we wanted to go backwards, we do negative to the negative 10 to the negative POH. Perfect. Now finally, how are pH and POH related at 25 degrees Celsius? 14, right? They add up to 14. So pH plus POH equals 14. Why 14? Why 14? What's special about 14? 14 is the negative log of Kw. The negative log of Kw is actually pKw, right? And so since Kw is 10 to the negative 14, negative log of Kw is 14. And that's why pH plus POH add up to 14, but only at 25 degrees Celsius, because that is the value related to Kw at 25 degrees Celsius. So the reason that this is called the magic square is because if you know one corner of this square, you actually know all four corners of the square. You know every single part, because all of these values are related to each other either by, Kw or pKw, all of those things. So these are the ideas that we're going to be constantly using, navigating. Oh, if, I give you OH minus concentration, we can back calculate to H plus concentration using Kw. So being able to navigate this square is very important. Okay, so that's the magic square from last time, but hopefully you've recognized that in this chapter. Okay, so let's start with chapter 16, possibly question 2. So let's look at question 2. Okay, am I recording? Yes, I'm recording. Okay. All right, let's just do 1 and 2, okay? So let's preface ourselves with, ice tables. Chapter 16 and 17, it has to do a lot with ice tables, chemical equilibrias. Let's collect all of the Ks that we've collected thus far. I told you that 1220 is the class of K, like big K. We talked about big K for like 3 months. What is Kc? C stands for concentration. That was on chapter 15 though, all right. Kp, what does P stand for? Pressure, all right. So that was chapter 15. So now let's do chapter 16 where it's specific to aqueous equilibrium. Okay, what does Ka stand for? Acid, you use that for weak acids. Kb, base, so you use that for weak bases. Kw, water, all right, Kw, the W stands for water. What else is there? Ksp, what does Sp stand for? Solubility product, so you're throwing a salt into water and it's dissolving. And then what's the last one? Kf, what does F stand for? Formation, you're forming a very soluble complex ion. Those are all of the Ks we're using. Mostly for this chapter, it's Ka, Kb, Kw, which are all related, Ksp, and Kw. Okay, so in this question, 1 and 2, we're talking about Ka, a weak acid. So here I have a solution of a hypothetical weak acid. It has a pH of 4. What is the Ka for this acid, Ha? So this is a weak acid, so we want to use an ice table for an acid. Since I'm asking you what Ka is, it would be best to write what is the Ka expression for Ha, this weak acid, putting it into water. Since we're putting Ha into water, I'm going to start with Ha breaks up into H plus and A minus. All of this is aqueous. I'm just lazy. I don't want to write the phases. Everything is aqueous. So everything goes into the Ka expression, right? So, we can write that Ka expression is H plus concentration times A minus concentration over Ha concentration. Products over reactants, right? So for this question, I tell you what is, here's the concentration, here is the pH, what is the Ka value for it? So this is very similar to a type 1 ice table where I give you a hint at the equilibrium line and it helps you fill in the rest of the table. So if we write out our ice table, 0.150 molarity is going to go in which line? Initial, change, equilibrium, we all quiet. It's going to go in initial, yeah, just like all ice tables. That's our initial concentration. 0.5 molarity, zeros everywhere else. In ice tables, which way does this reaction have to go? Forward, minus X plus X plus X. So after equilibrium has been established, we will have 0.15 minus X of HA, X of H plus, X of A minus. So we put those values into our Ka expression, x squared over 0.15 minus x. We want to calculate what Ka is. So we need to figure out what x is. What piece of information did we not use yet? pH. Does pH help us figure out what x is? Yes, because x is actually also equal to the H plus concentration at equilibrium. So x is equal to 10 to the negative pH that is given. That is what x is. So there's our hint at the equilibrium line. So we know exactly what x is. We plug it into the Ka expression to solve for Ka, because we know what x is. Would it be appropriate to do an approximation here? Why? Why should I not take away that minus x? I thought we do that all the time. Because we know what x is. What's the point of approximating? It avoids doing what? The quadratic formula. If you approximate here, if you get rid of that negative x minus x in the denominator, you're just being lazy. You know what x is. Just plug in the number into your calculator. So the full work here, 10 to the negative pH, what number is that? Did I write it down? It's just pH is 4. So that means that x is equal to 1 times 10 to the negative 4, molarity. That is the concentration of H plus. So x squared is 1 times 10 to the negative 4 squared over 0.15 minus 1 times 10 to the negative 4. You can solve that in your calculator, and that is Ka, and you get something like 6.7 times 10 to the negative 8. Okay, you know what x is, just plug it in. Okay, so that's number one. We use the Ka expression because we put an acid into water. So same thing for question 2. Pretend we have a hypothetical acid, docwinic acid. I name things after myself. And it has a Ka of that. Just think of this acid as Ha. Okay, don't get all bunched up because it's a different formula. It's still a weak acid. Let's just call it HA. And then here is the Ka value. So I'm asking you to calculate the pH and the percent ionization of 2 different solutions. Both of them will utilize the ice table. So I'll just do the ice table once, show the approximation, and you'll see how straightforward it is to approach a pH calculation when given a Ka and an initial concentration. So let's do the first one with an ice table. HA is an acid, so we're going to use the Ka expression. So HA breaks up into H plus and A minus. I hope this looks familiar. We write out our ice table where HA concentration is initially 0.1 molarity, 0 of everything else. This reaction has to move forward, so minus x plus x plus x. So at equilibrium, we have 0.1 minus x, x, and x. So we see that Ka equals x squared over 0.1 minus x, and this equals 1 times 10 to the negative 5. Does this require the quadratic? Yes. So do you want to approximate? Yes, let's approximate. And so when we approximate, we just get rid of that minus x. And so then when you solve for x is equal to 1 times 10 to the negative 3 molarity. But it's the molarity of what? What does x represent? H plus. Why is it H plus? Because we used Ka. H plus is x in the ice table, right? So that is for the first solution. So for that one, pH is equal to 3, right? So for this follow-up question, B, it's the same acid. I'm asking you the pH, but look, the concentration's more. So what does your intuition say about the acid? How will this new acid that's more concentrated, well, sorry, it's the same acid. The more concentrated one, will it be more or less acidic than our previous answer? It's going to be more acidic because it's more concentrated. Add more acid to solution, it's going to be more acidic. It's going to have a lower pH. So let's prove it. So in B, I hope at this point you recognize what the Ka expression reduces down to when you do the approximation. Ka equals x squared over the initial concentration, so 0.5. You don't have to do the whole ice table if you know you're going to approximate. All right, and this is equal to 1 times 10 to the negative 5. Solve for x, you get that x is equal to a different number, 2.2 times 10 to the negative 3 molarity of H plus. So if we compare these two numbers, yes, the more concentrated version has much more H plus present in solution. So when you pH that one, B, you get a pH of 2.7. So yes, this solution is in fact more acidic, right? So I got the pHs. So now the follow-up question is, okay, what about the percent ionizations? Right, so percent ionization is one of the equations we give you on the supplemental information. I'll do a different color. So percent ionization is H plus concentration at equilibrium over the initial concentration of the acid, the initial concentration, times 100 to make it a percent. So we actually have all the numbers we need to calculate this. H plus at equilibrium is actually X, the X we already calculated. So if we go back to these answers here, the percent ionization of A is 1 times 10 to the negative 3 over its initial concentration, 0.1. So we see that percent ionization is about 1%. All right, versus we do the same thing for B, the more concentrated one. Percent ionization is that 2.2 number that we got, divided by the initial concentration, 0.5 molarity, times 100, and we get that the more concentrated one is actually only 0.4% ionized. So what do we see here? Solutions are more ionized at what conditions? When they are high concentrations or low concentrations? Low concentrations, and the reason is this equation, all right? The percent ionization equation has two factors. H plus concentration, this is related to Ka, right? The more acidic an acid, the more ionized it's going to be because H plus at equilibrium is a large number. But the denominator actually has to do with the concentration of that acid. So we see if we have a big number in the denominator, the percent ionization comes out to be small. So higher concentrations are actually less ionized overall because you have a big number in the denominator. And I actually want to follow up on that. Let's do this question. All right, so we answered that question. Let's consider these two hypothetical acids, HL and HN. They're both weak acids. How do I know that they're both weak acids? Ka, I give you Kas for both of them. So based upon those Ka values that I give you, which one is more acidic, HL or HN? HL, why? The Ka is bigger, yeah. If you put both of these into water and they were the same concentration, HL will be more acidic because Ka is bigger. Both of them will just be x squared over whatever equals Ka. And because Ka is bigger for HL, x is going to be a larger number for HL. All right, so then which base is more basic? NaL or NaN? So these are the conjugates. So which one? NaN, yes. The weaker acid is going to have the stronger conjugate base. What we're actually doing in the background is comparing KBs, but I didn't actually do it, right? So here, you told me, okay, yeah, HL is the stronger acid because Ka is bigger. So let's compare the conjugate acids, L minus and N minus. So both of those are bases. What is the KB of L minus? Hopefully you can do this in your head. It's 10 to the negative 11, yes, because both of these numbers have to multiply to Kw. An acid-base conjugate pair are always related by Kw, not 14, 11, right? Then what is the Kb of N minus? Negative 8, yes, because negative 6 plus negative 8 is negative 14, right? So really what we're doing in determining that NaN is the stronger base is because its Kb is larger. Look at it. When you already have a weaker acid, its Kb is going to be larger. Basically, the smaller Ka is for an acid, the larger the Kb is for its conjugate base. So that's why we see, oh yeah, NaN, the conjugate base, is the more basic substance. All right, so then which solution is going to be more ionized at equilibrium? The same concentration of HL or the same concentration of HN? I will remind you, percent ionization is H plus concentration at equilibrium over initial concentration. Which one is more ionized? HL or HN? HL, it's HL. So let's look through this. How do we calculate percent ionization? It's how acidic the solution is over the initial concentration. Let's look at the denominator first. What is the initial concentration for both of them? They are the same. So is that going to differentiate it? Nope. So we want to actually look at the H plus concentration at equilibrium. You already answered this. Which acid is more acidic? Which one's going to have a bigger number in the numerator? HL. So that's why HL is more ionized, because its Ka is larger. They're both the same concentration. So I essentially forced the denominator to be the same for them, but here we're comparing Kas. So we see Ka is larger for HL. The numerator is going to be larger. Okay, next one. Other ways to conceptually ask basically all the same question. Which is the more stable conjugate base? L minus or N minus? L minus, yes. Stable conjugate bases make really crappy bases. If your conjugate base is really stable, it's fine being an anion. It doesn't need a proton, okay? Because what do bases do? Bases accept protons. So if you have something that's really unstable, something like methane where I ripped a proton off, that lone pair on that carbon is really not stable. It's really not stable. So that carbon atom, that lone pair, is going to grab whatever H plus is lying around. So this substance is really unstable, so it makes a really great base. But if you have a conjugate base that's really stable, it's not going to act as a base. It doesn't need an H plus. So in this case, L minus is the stable conjugate base because NaL is the less basic thing. All right. And then finally, the last one here, what solution is more ionized at equilibrium? Be very careful of what I'm giving you. It's 0.1 molarity HL and 0.01 molarity HL. So it's the same acid. So when we think about this equation, which thing is affecting us more, the numerator or the denominator? The denominator, it's the concentration. So which one's more ionized? The less concentrated one. All right, so that kind of rounds out that question. Okay, next. Numbers. No? No? Okay, then I'm just gonna go in order. Okay. Of this following structure of glycolic acid, I applied this to my face last night. Actives, skincare. That's something I like. Glycolic acid is an alpha hydroxy acid, an AHA, which is highly water soluble. So it penetrates deep into the skin and it helps promote cell turnover. So you get clearer, less, I guess, like scars on your face, less dark spots. That's what glycolic acid is great for because it's highly water soluble, versus salicylic acid is actually more oil soluble. It's a BHA, so it sits more on your face, better for inflammation and unclogging pores on the surface of your face. Has a lot to do with chemistry. Okay, but let's look at the actual question. So that's glycolic acid. Which proton is more acidic? Which one is more likely to be donated? 1 or 2? 2, yes, 2 is much more likely to be donated, but why? It's a carboxyl group. Carboxyl groups are very acidic, but here is the reason. And it has to kind of do with this idea. Stable conjugate bases that are really stable usually come from very strong acids. Strong acids make very, very stable conjugate bases. So if you think about, okay, if I rip the proton off of spot 2, all right, so I'm ripping that proton off, think about what's left behind. You have this group, which puts a negative charge on an oxygen, but this oxygen is special. It can also do what? Resonance. This can do resonance. So is that negative charge solely on this oxygen? No, it's actually smeared around this entire group. That's what makes this very stable. Versus, let's compare ripping hydrogen 1 off. Let's rip the first proton off. So rip that off, you're left with an H+. So now you're left with 3 lone pairs on just an oxygen. Oxygen, very electronegative, it pulls and attracts electrons, but is that negative charge, can that negative charge smear around the molecule like the other one can? It cannot. So this is much less stable. This is, I'm just gonna say less stable than this one. This one can do resonance, so that is resonance. So the second proton is very acidic because what's left behind is very stable. Right, so yeah, I guess which indicated proton is more acidic? It's proton 2, right? So then let me ask this question. Which thing is more basic? This? Or this? Let's say A and B. Which thing is more basic? Okay, acids donate protons, bases do what? Accept protons, right? It accepts protons by donating an electron pair, right? Lewis bases are electron pair donors. So think, which substance is more likely to accept a proton? Which one wants a proton back? A or B? A, yes, A wants that proton back real bad because its negative charge is not stabilized. It's really localized on that oxygen. So we can basically make everything charge neutral by adding an H+, then it's charge neutral again, and then it's stable and happy. Versus B, that's again a carboxylate group, where this on its own is very stable because it can do resonance. So see how our answers changed, because what I actually showed you are the conjugate bases. Here, I have 2 acids. I told you that an alcohol is a crappier acid than a H+ that's on a carboxylate group, or carboxylic acid. This is less acidic than this. So if we compare the conjugate bases, the conjugate base of the crappier acid is going to be the better base. So that's what we said here. A is the much better base than carboxylate because this is much less stable than the other substance. So the same thing applies here as well. Stronger the acid, weaker the conjugate base. Weaker the acid, stronger the conjugate base, and vice versa. Okay, so someone asked for question 22. Oh, actually, I want to do 10. Let's do 10. Let's just wrap this up. Which is the most basic? Let's remember our definitions of bases. A Bronsted-Lowry base does what? It accepts protons. But for completeness, tell me, what do Lewis bases do? Donate electrons. A base will do actually both of these things. So that's your hint. Because sometimes it's really hard to bases, they're always harder. Okay, acids are easy, weak acids, because in order to be an acid, it has to have an H, right? But bases, they're harder, because like, why is ammonia a base? It's because of that lone pair. That lone pair does what? It donates its electrons to an H+, where that H+ is accepted, all right? It accepts a proton. So that what makes ammonia a base. So really the kind of overarching idea of weak bases is if there's a lone pair present, it's much more likely to be a base. So if we look at all of these structures, which of the following is the most basic? Drawing the structures are going to really help, right? So NH4, does NH4 have any lone pairs? It does not. What about CH4? Does it have any lone pairs? No. So can either of those be bases? They cannot. So what is the only thing that can act like a base? Water. Water is the only thing that can act like a base because it has those lone pairs. And that's weird because water, we think of that as neutral, but it can still act as a base. It can still grab a proton, all right? It can grab that proton to make H3O plus hydronium, and that's a reaction that happens. So yeah, in this case, water is the most basic. All right, the other two substances can never act like a base. There's no spots for it to accept a proton because there are no lone pairs. All right, so someone asked for question 22. Okay, let's do 19. Oh wait, 22. Hold on, 22. And let's just do the KSP, all of them. All right. Okay. So KSP is much different than acids and bases that we've done before. I don't know. Do you think it's easier or harder than like buffers and stuff? Easier? Okay. Yeah. So the whole idea is writing a KSP expression. That's kind of the hardest part, but it's even not that bad because there's never a value in the denominator, which is nice. So here are three substances, and I asked you to order them in increasing molar solubility. So you might just look at these KSP values and think, oh, B, this one is the most soluble because KSP is the largest number, versus C is has the lowest solubility because it's the smallest number. We can't do that. We actually have to solve for X. So KSP is the constant, the solubility product constant, but molar solubility actually represents X from the ICE table, right? So you actually have to solve for X in the ICE table for all of these substances, but it's not that bad, it's pretty repetitive. So when you write out a KSP expression for AB, this is the general form, you throw AB solid into water, it splits up into what? A plus and B minus. Those are both aqueous. So when you draw out an ICE table, you throw a random amount of solid in. It doesn't matter how much, just a chunk. So some of it dissolves. So that means you lose an X amount of the solid. But that also means you gain an X amount of A plus and B plus. So at equilibrium, you have N minus X of AB, X amount of A plus, X amount of B minus. What is the KSP expression for this? Not in terms of X's, use the actual chemical formulas. It is equal to A plus concentration times B minus concentration. Is there anything else in this KSP expression? There is not. This solid does not go into it, right? So that is our KSP expression. What molar solubility is this minus X. So yes, I said that we don't actually have to put N minus X into our KSP, but that X is what represents what molar solubility is. It's how much of this solid we lose when we dissolve it in water. So how much of the solid do we lose in terms of mole for every 1 liter of volume? So we can't measure that directly because it's not in KSP, but X shows up in other places, and that's what we're going to utilize here. Because like all ICE tables, we shove our E line into KSP. So KSP for this example equals X squared. We set that equal to the KSP value that's given, and we just solve for X. So in this case, I think I can do this in my head. X equals 1 times 10 to the negative 5. And these are the numbers we want to compare, what the X values are. Right? So for the next one, KSP, is this, so if we put this in terms of molar solubility, so I'm gonna just move this over there, all right? This KSP expression, you dissolve AC2 into water, It doesn't dissolve in a 1-to-1 ratio. It does not. So if we wrote this KSP expression, it would be A 2 plus concentration times C minus concentration squared, right? When this breaks up into water and we do our ice table, we get an X amount of A, but then how much C do we get when it breaks up? 2X. So those are the X's that we put into our KSP expression. So this KSP expression reduces down to X times 2X squared. So this is actually equal to 4X cubed, and that is equal to, I need to delete all this, the 1 times 10 to the negative 8. So we need to divide by 4 and then take this to the 1/3 power to undo that cube. Or you can do the cubed root, but that's hard to find on your calculator. Same thing, 1/3, 1/3. The exponent is the same thing. So you get, in this example, X is actually equal to something else. I can't do that in my head. It is equal to something else, 1.4 times 10 to the negative 3 molarity. All right, and now the last one. So the KSP for this last one is A concentration times D concentration, but cubed. Now put this in terms of X's, molar solubility. You throw a chunk of A, D3 into water, you gain an X amount of A, but then how much D do you gain? 3X, so that's where the stoichiometry shows up. So that means when you put these values into the KSP expression, 1 times 10 to the negative 15 equals X times 3X cubed. 3 cubed, I think, is 27. So 27X to the 4th. So to solve for X, divide both sides by 27, take this to the 1/4 power, and you get that X is equal to 7.5 or 7.8 times 10 to the negative 5. Okay, so in this example, you know, we actually have to solve for X because we're comparing molar solubility. We can't just look at the KSP values. We've got to look at the X values because there are different formulas. Right. Yeah, we're doing all the KSP ones. We're just going in order. Okay, so the next one. So in this example, we are throwing a solid into pure water and seeing how much of it dissolves back into the water. So we are describing saturated solutions. This is that dynamic equilibrium we talked about in chapter 13, but we kind of skipped over. This is what we mean by it. A saturated solution is dictated by KSP. So any saturated solution will have that KSP. So that means if you mix things, if you mix like A concentration and B concentration, and you calculate Q for those conditions, if Q is greater than KSP, you have too much product, a precipitate will form, that a solid will come out. But if you have an example where Q is actually less than K, no precipitate will form. It will just remain a colorless solution. If you have concentration and Q is equal to K, KSP, so all this is KSP, then you're already at equilibrium, you already have a saturated solution. So that's the whole idea here, all right? So that's what's kind of being shown in kind of question 20 is, okay, we have a mixture of magnesium and aluminum. We add small increments of sodium hydroxide. Which solution will precipitate out first? So we can quickly write out what the KSP expressions for this are. We have magnesium 2 plus times hydroxide minus concentration squared. For aluminum, it's aluminum 3 plus times hydroxide concentration, but it is cubed. So I'm telling you what the concentrations of the metals are. I'm setting those. So I want you to tell me what is the minimum required amount of hydroxide required to get to that KSP value. So we can solve for that because we know KSP, we know the metal concentration, we just solve for hydroxide concentration. right? So I think when you do that for magnesium, the hydroxide concentration required is something like 1 × 10⁻⁵ molarity hydroxide. But if you do it for aluminum, you see that hydroxide concentration required is something like it's something like 0.046 molarity hydroxide. So these are the two numbers we want to compare. So if we add tiny, tiny amounts of hydroxide at a time, which concentration will we reach first? The smaller one or the bigger one? The smaller one. So we will reach this concentration first. So that means if we reach this concentration first, we will fulfill the KSP for magnesium hydroxide first. So in this example, magnesium hydroxide precipitates out first. Or you can think about it this way. You know, I think in the key, I wrote that this is a pH of 9, while the other one is like a pH of 12. You don't actually need the pH to solve this question. If you just think about it, like if in your burette, you start with like neutral, pH neutral water, and you add sodium hydroxide in small amounts, which pH will you reach first? A pH of 9 or a pH of 12? 9. You're gonna work your way from 7, work your way up. So in this case, magnesium at a pH of 9, that's when everything will precipitate out, because now your Q is greater than K at those conditions. How do we get concentration? I solved for this. I know this number. I set it equal to magnesium. I know that number. We solve for hydroxide. There's one variable, solve for it. So you have to take the square root. So magnesium concentration is given in the question at 0.1 molarity. Okay. So, all right, so let's move on to the next question, people asking about common ion effect. And so in all the previous examples, we made saturated solutions, we made solids. So the question is, how can we affect the solubility of things, right? So, you know, we talked about this in chapter 13, where usually solids are more soluble at higher temperatures, right? Using concepts that we learned about in this chapter, why do you think solids are more soluble at higher temperatures? What is changing? KSP is changing. How is the value of KSP for a solid changing when you increase the temperature? It's probably getting bigger. And that's why things get more soluble, because KSP changes. But there are other ways we can affect the solubility of things. There are 3 ways we can affect the solubility of solids. The first one is common ion effect. All this is just fancy footwork with Le Chatelier's principle. The second way is pH changes, but pHs only affect some things, and I'll point that out in a second. And then the last one is complex ion formation, so KF. Right? So the trends are common ion effect decreases solubility, or X, I guess, like it decreases your molar solubility when you do a KSP expression. You decrease the amount of stuff that dissolves, so typically more solids come out. pH typically increases the solubility of stuff, but not everything, just some things, right? Complex ion formation also increases solubility of things, but only some things, things that can form complex ions. That's the trend, but really what it is fancy Le Chatelier's principle. So let me show you an example. What if I had AgF solid, right? That has a KSP. So if we write that KSP expression, this breaks up into silver plus and F minus. Right? So pretend we have a saturated solution of this stuff. What does Le Chatelier principle predict if we add H plus? Which way does it shift? Backwards. So what should you observe with your eyeballs? Solid comes out, right? It's more solid forms. So what does that say about the molar solubility when we add Ag plus? Molar solubility decreases because more solid falls out, that it's less soluble when Ag plus is really present. So that is why Common ion effect decreases molar solubility because adding A plus or Ag plus pushes the reaction backwards to form more solid. Typically when we do KSP, it's negative X plus X plus X. So if we add Ag plus, this minus X is going to be a smaller number now that a common ion is present. It pushes the reaction backwards, makes it less soluble. Same thing with F minus. What if we add F minus to solution? Does it make this solid more or less soluble? Less, because it pushes it backwards. That's what Le Chatellier's principles say. What if we have a saturated solution and we remove Ag plus? What happens? The reaction shifts which way? Forward. What do your eyeballs see? Less solid. So what can we say about molar solubility? It increases. Same thing with F minus. What if we remove F minus? Same thing. Reaction moves forward, things become more soluble. So I mentioned this because when we added those common ions, that's the common ion effect. But when we remove these products, that's where pH changes and complex ion formation takes into place, because those are ways we can essentially remove them from the chemical equilibria. So how pH changes affect molar solubility, all right? So the question is, and I already asked you, if we remove F minus, you told me that the reaction shifts in the forward direction, becomes more soluble. But how can we remove F minus? F minus is a base, isn't it? Bases do what with acids? They become neutralized. So if we add HCl to this, HCl is a what? Acid. HCl is going to react with F minus, essentially removing it from the equation, removes it from the equation, right? So here we see this compound gets more soluble at lower pHs. It becomes more soluble in acidic conditions because its anion is a weak base. Another example would be like magnesium hydroxide, right? Breaks up into magnesium 2+ and 2 hydroxides. Right? If I add acid, H+ is going to react with what in this chemical equilibrium? OH-. If these two neutralize one another, you're essentially removing hydroxide from that reaction. So again, Le Chatelier's principle, what happens when you remove a product? The reaction shifts forward. So magnesium hydroxide is more soluble in acidic conditions. Have you ever done the experiment where you soak an egg in vinegar? No? Yes? What happens to the egg? The shell dissolves. What is vinegar? An acid. And now I have to tell you, eggshells, they are made of calcium carbonate. Calcium carbonate. So what is the KSP of this? Calcium 2+ and carbonate 2-. So when you soak an egg in vinegar, that acid from vinegar, acetic acid, is reacting with what? The carbonate. The carbonate. So what happens to this chemical equilibria in the presence of acid? It shifts to the forward direction. So you see the solid dissolve, and that explains why when you soak an egg in vinegar, it slowly, the shell dissolves away, right? So I don't know what grade we do that demonstration, I don't know, but it has to do with KSP and effects of solubility effects. Okay, so there we go. So that's common ion, pH changes. Things will become more soluble in acidic conditions if the anion is a base. It could be a weak base, like F-, acetate, carbonate, those are all weak bases, or it can be like straight up hydroxide. Okay, because acids react with bases. And then the last one is KF formation. So the same reason that I said, okay, I have this chemical equilibria. If I remove F-, it shifts forward. I can also say, oh, if I remove Ag+, it also shifts forward. So I can use KF to say that. So I would tell you, okay, here's the KSP for this compound, the KF, or the KF, or let's say silver ammonia complex is equal to a really large number. I'm just going to make something up, 10 to the positive 17, right? So I might give you this Kf value, but what you should infer from this is, oh, if I add ammonia and Ag plus together, they will react to make a very soluble complex ion. So in this saturated solution, I have a little bit of that Ag plus. So if I add ammonia to this reaction, just like H plus reacted with a base, ammonia is going to react with Ag plus. And I know that because its Kf is a really large number. So essentially adding ammonia removes Ag plus from this reaction. So if I remove a product, which way does the reaction go? Forward. The solid becomes more soluble. So it's the same reason. So Kf and pH changes, you're adding something to the reaction that basically consumes a product, so it makes the thing more soluble, right? And so I know adding ammonia will make a complex ion because it's literally in the complex ion equation that's given here. I'm not going to give you like some random thing, right? Versus, what if I added NaCl to this to the Kf expression, to a saturated solution of silver fluoride? What's going to happen if I add NaCl? Is anything going to happen? Are there any common ions? There are not. Na plus, Cl minus, Ag plus, F minus. There are no common ions. NaCl, are we changing the pH? Nope, that's a neutral salt. Is NaCl part of any complex ion? Nope. So adding NaCl will actually do nothing, because there are no complex ions, there's no pH changes, there's no complex ion. Okay, so let's actually answer this question. So which would be an example of pH dependence of solubility? Select all that apply. Okay, so pH dependence, if anything, just remember, add acid makes a basic salt more soluble. All right, add acid, basic salt becomes more soluble. All right, so will adding HCl to saturated calcium hydroxide make it more soluble? Yes or no? HCl is a acid, calcium hydroxide is a base. So yes, that is going to make it much more soluble in water. Adding HCl to saturated ammonium chloride, is that an example of pH dependence? HCl is an acid. Ammonium chloride is actually a what? Also an acid. So that is not, adding two acids together, that's not going to affect solubility at all. Actually, what does that exemplify? That is actually the common ion effect, right? There's a common ion effect there because it's chloride, but that doesn't increase solubility. Right, so adding HCl to ammonium chloride will make it less soluble, in theory. All right, so adding HBr to calcium carbonate. HBr is a what? Acid. Calcium carbonate's a what? Is it a base? It's eggshells. Eggshells, yes. It's eggshells. So yes, C is also. That's the dissolving eggshell egg thing. Does anyone remember doing that demo or that experiment? What else did you see when you soaked the egg in vinegar? Did you see anything else? Like, yes, the shell dissolves. Was it bouncing? It was bouncing probably because bubbles were being formed. What bubbles do you think those were? It was CO2. Yes, it's CO2 because of carbonate. All right, adding HBr to saturated calcium bromide. Is that pH dependence? No, that is actually what? Common ion, yeah. So adding HBr will actually decrease the solubility of calcium bromide, not increase it. HCl to calcium chloride. That one is also common ion. So again, that's nothing. Let me do one more. What if I did HCl and calcium bromide? Is that pH dependence? HCl is an acid, but calcium bromide's a what? It's pH neutral. Yeah, so bromide is not a base. It's a pH neutral salt. So this actually has no effect. HCl won't do nothing to its, because there's not even common ion effect happening here. All right, 23, what would be an example of complex ion formation effect on solubility? So remember, complex ion formation typically does what to the solubility of things? It increases things. So adding sodium hydroxide to aluminum 3+ to produce the aluminum hydroxide complex. Is that an example of complex ion formation? It is, because we are forming an aqueous complex. This is the complex. The thing that is aqueous. Because typically when we combine metals and hydroxides, they typically make solids, kind of like the next one. Adding sodium hydroxide to aluminum 3+ to produce aluminum hydroxide solid. Is that complex ion formation? That is not. That's a solid. Complex ions are aqueous in solution. So really, this is describing KSP. So that is not complex ion formation. Great. Adding HCN to saturated rust to form an iron cyanide complex. Is that complex ion formation? Yes, it is, because again, you are forming a complex. What about forming rust? Is that complex ion formation? No. So only 2 of these things actually are utilizing KF in some extent, that we're combining a cation and an anion to form a soluble complex ion that's aqueous. All right, now finally, all right, so that was complex ion, pH things. Which solids from this list are more soluble in acidic conditions? This is really an application of chapter 16. Remember in the SAL lab, the chapter 16, we asked you, I give you a bunch of salts and I ask you, is this salt acidic, neutral, or is it basic? Same exact skills here, right? Adding H+ to a salt that is basic, meaning that the anion is a base, will make it more soluble. So really what you're doing here is asking yourself, am I looking at a acidic salt, a basic salt, or a neutral salt? Acid, changing the pH will only make things that are basic salts more soluble. So let's look through these. Iron chloride. So maybe just ask yourself, what kind of compound is that? Is that acidic, basic, or neutral? It is acidic. Why is it acidic? What part of it makes it acidic? Iron 3+. Iron 3+ is what kind of acid? A Lewis acid. You might be thinking, oh, that's not a weak acid I've ever seen before, but it's a special kind of Lewis acid. Let's go through the rules real quick. So this is actually chapter 16 review as well, right? Where I give you a substance and you have to predict whether it's acidic, basic, or neutral. So there's kind of some ground rules here. You want to be looking for conjugates of weak things, but keep in mind that there's a handful of pH neutral things, all right? So looking at it on the cation and anion side, if you have something that's pH neutral, you literally ignore it in terms of pH, like acidity, okay? So cations, common pH neutral cations, all group 1A elements, all group 2A elements. So lithium plus, sodium plus, potassium plus, all of those are pH neutral. Then we have calcium 2+, magnesium 2+, etc. The reason these are pH neutral, pH 7, when you put those in water, is because they are conjugates of strong bases. So same idea. If you look at the anion side, the conjugates of strong acids are pH neutral as well. So common ones, chloride, bromide, iodide. Those 3 anions are pH neutral because HCl, HBr, HI are what? Strong acids. So what's another strong acid? HNO3. So that means nitrate is what? pH neutral, because nitric acid is a strong acid. The other one, ClO3 minus and ClO4 minus, right? All of those are pH neutral. So remember, How many strong acids are there? 7, but I only have 6 on this list. All right, so you might be wondering, oh, is sulfate a pH neutral salt? It is not, and here's the reason. Okay, do you remember in Chem 1220 or 1210 when we said, okay, sulfuric acid is a strong acid, but what was the caveat? Only the first proton is strong. So when the first proton comes off of sulfuric acid, you make HSO4 minus. Is HSO4 minus a strong acid? No, it's not, because I said only the first proton is strong. The second proton is weak. So this has a Ka value. So if HSO4 minus is a weak acid, that makes SO4 2 minus a what? Base. Yeah, so sulfate is actually a base, slightly basic, it's a weak base. So, but if you just want to memorize it, all right, just remember that only 6 of the strong acids have conjugates that are pH neutral. Sulfate is the exception. Do not include that one. That one's not included. So it's only the monoprotic ones. These 6 are pH neutral. So that means we can ignore them. So basically, I told you, those are the list of things that you can ignore. So an iron chloride, we looked at iron. Do you see why we can just ignore chloride? Because that's pH 7. What about B? What is this? Acidic, basic, or neutral? It is basic. Why? Calcium? Is it because of calcium? Nope, that is pH neutral. We can ignore that. So what we're actually looking at is CN minus. CN minus is a what? It is a weak base. The reason is because HCN is a weak acid. So CN minus has to be a weak base. So let's go back to our question. If calcium cyanide is a weak base, will it become more soluble in acidic conditions? Yes, it will, because it's a weak base. That H plus is going to react with cyanide to make HCN. So you're going to be removing it from the reaction. All right, AgF, acidic, basic, or neutral? Basic, why? F minus, so that also is going to be more soluble in acidic conditions. Lead chloride, acidic, basic, or neutral? It's acidic because of lead 2 plus. All right, it's another Lewis acid. So is that going to be affected by adding H plus? It is not. So that one's boop, nope. Calcium hydroxide. Yes, that is it's literally a strong base. So calcium hydroxide, yeah, if you add H plus, it's going to react with that hydroxide, removing it from the reaction, making the thing more soluble. Strontium perchlorate, acidic, basic, or neutral? It is what? It is neutral. Sorry, strontium is in group what? 2A. Chlorate, is that one of the 6 pH neutrals? Heck yeah, it is. Just memorize them. But you don't really need to memorize them. If you already know what the 6, 7 strong acids are, all right, it's already there. You just have to know the conjugates of those are pH neutral, except sulfuric acid. All right, magnesium phosphate. Acidic, basic, or neutral? Basic, yes. Why? Phosphate. Phosphate is like the super conjugate of phosphoric acid, H3PO4. That's a weak acid. So those protons, very difficult to pop off. So phosphate has to be a weak base. Yes. Aluminum hydroxide. Also basic because of that hydroxide. So magnesium phosphate, basic, aluminum hydroxide. Basic. So you're looking for weak things, conjugates of weak things. All right. Okay. So that's all the KSP stuff. I want to do buffer stuff. We got 30 minutes. Let's do buffer stuff. So, okay. So I do give you, yeah. You said magnesium and strontium are weak bases? So the acidity of silver does not react with H+. Yeah, so we're looking at H+ reacting with weak bases. Yeah, that's a good question. So let's just work through how we would do some buffers. Let me talk about some misconceptions that I constantly see. All right, what is this? pH equals pKa plus log base over acid. What is that? The Henderson-Hasselbalch equation. You all love to use this equation for all scenarios. You love to just shove numbers in there all the time, even if it's not a buffer. But we only use this equation when it's a buffer. So the idea here is, well, the mixture that I'm mixing together, is it a buffer or not? Because if it's not a buffer, you use a different way to calculate the pH. This equation only works when we have a buffer. Buffers exist when, so I know in this base to acid ratio, I like made it simple, right? Base to acid ratio. It can't just be any base and any acid. It actually has to be the conjugate at base and the acid form. So the acid HA and the conjugate base. You have to have both of them present in large amounts. You actually have to have molarities of both of those, or you need to have millimoles of both of those. You have to. If one of those values are 0, you can't use the Henderson-Hasselbalch equation. It's not a buffer. You got to calculate pH some other way. If you shove it into Henderson-Hasselbalch, you will be wrong. So identifying whether something's a buffer is very important. So it can be A- over HA, or it could be something like a base, like ammonia over its conjugate acid, NH4+. Right? What you can't do is put, sodium hydroxide millimoles over HA millimoles. You can't do that, because is sodium hydroxide the conjugate base of HA? It is not. So when you combine these two things, you actually have to do a neutralization first, then put those numbers into the Henderson-Hasselbalch if it's still a buffer. All right, so that's the big idea. Base to acid does not mean any base, any acid. It has to be a conjugate acid base pair, has to. All right, so you got to figure out how much of that stuff you have present. So ask yourself, when I add these two things together, I'm adding 100 milliliters of acetic acid and 5 grams of sodium acetate. Does that represent my base to acid ratio for Henderson-Hasselbalch? It does, yeah. HA, that's acetic acid. Sodium acetate, what is that? That's A-. It's technically NaA, but I need to just convert those into millimoles. That's the first thing. I can't just do 5 over whatever. I actually have to convert how much of those do I have. So I like to work in millimoles because I'm lazy. So 100 milliliters times 0.2 molarity, what is that? 20 millimoles of HA is present in this solution, and we're mixing it with 5 grams of sodium acetate. So, we haven't done one of these in a while. 5 grams, use molar mass to convert that to a mole amount. So 82 goes where, on the top or the bottom? On the bottom, yes, 82 grams, 1 mole up top. So it looks like this solution has, has 0.061 moles of A-. So that means my base to acid ratio, I need to actually put this into moles. I can't say in millimoles. So this is 0.020 moles of HA. My base to acid ratio is 0.061 over 0.020 moles of each. That's moles of A-, moles of HA. That is what you put in your Henderson-Hasselbalch. pKa is equal to 4.74, and that's your pH. All right, so 4.74 plus log, that number will give you your pH, right? I'm just gonna do the setup. I'm not gonna do the calculations. The whole idea is getting that base to acid ratio. Okay, next one, pyridine and pyridinium chloride. Pyridine is a what? If you don't know, just look at the information given. I give you the what of pyridine? Kb. So pyridine is probably a base. So therefore, pyridinium chloride is probably its conjugate acid, so Hb+. So if I convert both of these into moles, using the molar mass, can I put those into the base to acid ratio directly? Yes, you can, right? Because you're adding the base, you're adding its conjugate acid. So now, are we gonna do one where it changes? Yes, so let's do this one. Okay, we're mixing acetic acid and sodium hydroxide. So let's get the millimoles of that. Okay, 50 times 0.2, is that 10? 10, I don't know. 10 millimoles of acetic acid, that's HA. And we're mixing it with what? 5 times 0.2, what is that? 1, is that 1? 1 millimole of sodium hydroxide. So does this mean my base to acid ratio is 1/10? It is not, because the base has to be what? A-. It can't be sodium hydroxide. So what's going to happen is, because we don't have A-, this has to react first. So you actually have to do a BCA table. But it's fairly straightforward. It's always a 1-to-1 ratio. Once you do like 3 or 4 of them, you'll recognize the pattern, all right? But I'll do the full BCA table. When HA reacts with sodium hydroxide, you make sodium acetate, the conjugate base, and water. All right, I'm missing some stuff. So let's just make this A-. There we go. There we go. This is your neutralization reaction. You combine an acid, a base, an acid and a strong base, you make its conjugate acid, or sorry, conjugate base, and water. So we're gonna do a BCA table. Use those millimole amounts. If I start with 10 millimoles of HA, 1 millimole of sodium hydroxide, which one's my limiting reactant? Hydroxide. So -1, +1. And we add water too, but that's not going to affect our pH. So after this neutralization reaction, we actually only have 9 millimoles of HA and 1 millimole of A-. So what is my base to acid ratio I need in this buffer? Is it 1/10? Nope, it is 1/9, because we have to do that BCA table first. Sodium hydroxide, you don't put that straight in the BCA table, or in the Henderson-Hasselbalch. You have to neutralize it first to make A-. A- is what goes into base to acid ratio. Okay, next one. Is this the same thing? No, it's not. Okay. So what are we mixing together? 10 millimoles of acid, HA. And then what is this? 1 millimole of HCl. Is that a buffer? No, what is it? It's 2 acids. So how the heck do we calculate the pH of that? Use which one? The strong one. So if you just figure out how much HCl is in this solution after mixing it, that's how you get the pH. So it's 1 millimole of HCl over, what's the total volume? 55 milliliters. And then whatever that H+ concentration is, get your pH. So you're essentially going to ignore that weak acid. Right? Okay, keep going. 40 milliliters of pyridine, 10 milliliters of HCl. Pyridine is a what? Base, because I give you a Kb. So if we get these millimole amounts, millimole of pyridine, I think this is 6 millimoles of base. This is what? 1.5 millimoles of HCl. So does that mean my base to acid ratio is 6/1.5? It is not, because I'm adding HCl. So what does that mean? After this neutralizes one another, neutralize, how much base do I have left over? I try to make the numbers easy. It's going to be 4.5 millimoles. But then how much conjugate acid do I have? 1.5 millimoles. So that is my base to acid ratio that I use. right? A neutralization reaction happens when we have a strong acid or base is being, so this is like a titration. All right. All right, pyridinium chloride and sodium hydroxide. So what are the amounts? 6 millimoles of pyridinium chloride. Is that a base or an acid? It's an acid, yeah, so this is Hb+. And then sodium hydroxide, this is what, 1.5 millimoles of sodium hydroxide. So does that mean my base to acid ratio is 1.5 over 6? It is not. We have to neutralize. So what is left over after you neutralize? How much base do you have? 1.5. And then how much conjugate acid do you have left? 4.5. So again, a neutralization is happening because there is a strong base being added. Strong bases react with acids. And so there's our base to acid ratio, 1.5 over 4.5. All right, keep going. HCl and sodium hydroxide. Is this a buffer? It is not. So is it useful for us to calculate the base to acid ratio? No. But do we still need to do a BCA table? Yes. So when we combine these things, how much HCl is here? I think 10 HCl. And then how much sodium hydroxide? 11.25. Why didn't I make the numbers easy? I don't know. All right, hopefully you don't have to do a full BCA table to figure out what's left behind, but I'm gonna do it anyway, because I think it's important. So when HCl reacts with sodium hydroxide, what do you get? Water and what? NaCl. So I'm gonna put the numbers in, and I'll show you that when we have 10 millimoles of HCl, 11.25 millimoles of sodium hydroxide, which reactant is left over? This solution, when we mix these things together, is going to be really what? Acidic or basic? Basic, because hydroxide is what's left over. But let me prove it to you. So minus 10 for HCl, minus 10 for sodium hydroxide, plus 10 for water, plus 10 for NaCl. So after this neutralization, I have no acid left, but I have 1.25 millimoles of sodium hydroxide. I have 10 millimoles of water, and I have 10 millimoles of NaCl. NaCl is a what? Neutral salt. Water is water, it's neutral. Sodium hydroxide is a base. So which one's gonna dictate our pH? The base, yeah. So all we have to do is just figure out, okay, take this substance, what is its concentration? This is chapter 16 stuff from last chapter. What is the hydroxide concentration? All right, that's left over after this neutralization reaction, and that's how we get our pH. So here, after the reaction, it's 1.25 millimoles, but what is the volume I divide by? It is 85, because that is the total volume of this solution. And so you get that the hydroxide that's left over in this reaction is 0.0147 molarity hydroxide. So I get, if I negative log that, I get 1.833. Is that my pH? Nope, that's pOH. So our pH is actually 12.167. Yes, super basic, because sodium hydroxide is left over. Okay, 17 and 18. So I got 10 minutes left. 17 and 18. I want to do 12. Okay, so we'll just keep going. All right, so if we want to prepare, so now we talked about like calculating buffers. Some of these were buffers, some of them were not. Let's say we want to prepare 500 milliliters of an acetic acid sodium acetate buffer with this pH, 4.85. How many moles of sodium acetate do we need to add to 0.25 moles of acetic acid? So here, this is a buffer. So we're absolutely using the Henderson-Hasselbalch equation, pKa plus log base over acid. I know the pH I want. I know the pKa of acetic acid. I hope at this point you know what the pKa of acetic acid is. What is it? 4.74, yeah. Log base over acid. We are solving for which thing? Base. Yeah, so I'm adding acetic acid, or sorry, I already know how much acetic acid I have. So I'm just solving for how much sodium acetate I have to add. So 4.85 equals 4.74 plus log base over acid 0.250 moles. So just solve for base. That will tell us B equals the moles of sodium acetate, the conjugate base that we need to add to this solution. So let me just go ahead and solve for that. So in this question, nope, that's not it. All right, so the base to, I think if you solve this like log base over acid equals something like 0.11. So that means my base to acid ratio equals 1.29. So if you just use a ratio, base over acid, which we know is 0.25. So we know, oh, for the base, we need to add something like a little bit more, 0.323 moles of base. That's how we achieve a base to acid ratio of 1.3, right? This question, straightforward, because I give you HA, I just ask you A minus. But is that the only way you can make a buffer? No, you can make a buffer by adding sodium hydroxide. So I can ask this question differently. Let's say we want to, actually I don't want to do that one. Let's do 14 instead. Okay, let's say, let's say we have a buffer, 500 milliliters of buffer, that's 1 molarity acetic acid, 1 molarity sodium acetate. The Ka is that. So that means the pKa is 4.74. What is the pH of this buffer right now? 4.74. How'd you do that so quick? Base to acid ratio is 1. Perfect. Let's say we add a tiny bit of HCl to this buffer. What's going to happen to the pH? It's going to go down. But by how much? So we got to figure it out. We got to do a BCA table. So we need to take from these pieces of information, oh, I have 500 milliliters of a buffer. How many millimoles of HA do I actually have? Because you told me, oh yeah, the base to acid ratio is 1. But technically, if we want to be really specific, how many millimoles of acid are present? 500. 500 millimoles of HA. How many millimoles of the base are there? 500. Okay, millimoles of the base. So really, yes, the base to acid ratio is 1, but it's actually 500 over 500. Because when we add HCl, how many millimoles of HCl are we adding? 10 millimoles of HCl. Look at these numbers. Acid is going to react with which one of these things? Oh, that shouldn't be a base, that should be A minus. Okay, so HCl is going to react with which one of these components? HCl is an acid. It's going to react with bases. Yes. So if you think about this, A minus is going to react with HCl to make more HA. This is not balanced at all, whatever. So when you do your BCA table, think about this. Our buffer initially has 500 of A minus, 500 of HA. We're adding 10 milliliters of HCl. So what are the new numbers after this neutralization reaction? We have 490 millimoles of A minus, and then now we have 510 millimoles of HA. This is how a buffer works. When we add acid, instead of going directly into changing the pH like crazy, what we're doing is just changing the base to acid ratio a little bit so the pH doesn't change that much. So this is my new base to acid ratio. So the pH of this solution after adding 10 milliliters of acid is equal to 4.74 plus log, what number goes on top? 490 over 410 or 510. And so when you calculate this new pH is something like 4.72. So did the pH go down? Yes, but did it go down a lot? No, because that's what a buffer is. all right? I want to do one more, because here I gave you a buffer that has is made of 500 milliliters. So let's just do another one real quick. All right. How is 15 different? It's still 500 milliliters, but what's the difference? What are the concentrations of our stuff? There's less concentration, so it's less concentrated. So if I do the exact same thing, tell me, what is the pH of this buffer? 4.74 again, yes, because its base to acid ratio is 1. But the difference is how many millimoles of HA are present right now? Initially, 50 millimoles of HA. And then how many millimoles of the base are there? 50 millimoles of A minus. So we can see, oh yeah, that base to acid ratio is still 1. But when we add 10 millimoles of HCl, what is the new base to acid ratio? It went from 50 to 50, but now it's actually going to be, so it was, 50 millimoles A minus, 50 millimoles HA. If we add H plus, all right, we're going to consume some of that A minus, so now it's going to be 40 millimoles of A minus, and now the denominator is what? 60 millimoles of HA. So what does our intuition say? When we add acid, how should this pH change? It should go down. But how is it going to go down differently than the previous one? It's going to go down more because there's literally less moles of stuff to be neutralized. And you can literally prove it to yourself right now that you do this. pH equals pKa, so 4.74, plus this new log base to acid ratio, 40/60, and you get that the new pH is actually 4.56. So did the pH go down? Did it go down more than the more concentrated example? It did, because there's less moles of stuff here. All right, okay, so best of luck on everything. If you still have questions on some of the questions, I suggest looking at the key.